upload this. And I'm going to share my screen so we can start on chapter 3 continuation, or chapter 3 part 2. Okay.
We're not to do that.
Huh?
Aren't doing thing anymore.
Yeah, we will be doing that. I will be doing that. But see, because you took a quiz, I know you're here.
Oh.
So it's more important when we're not doing quizzes, but yeah. And let me go ahead and make sure the chat's up so people can comment. And I'll leave the chat over here. And I think I want to extend my, huh? Oh yeah, this is total COVID deaths per day. Real data, real time. So unfortunately, it's on the rise again, which is why I'm wearing a mask. But that's not what I want to show you. I want to be on this page here. Okay, there we go. All right. But yeah, the world meter does deaths, births, and everything. It's like just raw data from whatever governments put on there. They have COVID and then they have a whole separate page for COVID, but it's births and deaths, population. You can go to any country in the world and figure out how many people there are, or how many people per 1,000 died of COVID or had COVID or all those things. It's really cool.
What's that called?
Huh?
What's it called again?
It's called World Meter. Worldmeter.org. Yes, data. So if you like data, you can do running averages, 3-day averages, 7-day averages, and see if it's trending up or down. It's really cool. Okay, let's get back to our data though. We were talking about things that can happen. And you all went to Canvas and downloaded the 5 things that can happen in the mechanism, right? And you did not tattoo it to your arm because you can't use that arm during a quiz. But we talked about those 5 things you can do. Add a proton, take a proton away, have a nucleophile react with an electrophile. We're going to, positive charge and a negative charge. Break into a molecule, which we just talked about on our last slide last time, and rearrange. So those are the things that can happen, okay? So we talked about all those, about rearrangements, about different types of reactions. So those are the things that can happen in the mechanism. We discussed 4 types of reactions. We talked about addition reactions, where we add something to it, elimination reactions, where we removed it, substitution reactions, and then we talked about breaking the bonds. We talked about homologous or heterolysis, homolytic cleavage or heterolytic cleavage. And in all of those, that gives us an idea of those things that can happen in the mechanism. So the next thing I want to talk about, though, is acids and bases. Now, in organic chemistry, we use slightly different terms for acids and bases than what we see here in your Gen Chem. Okay? In Gen Chem, it was always what we call an Arrhenius acid or base, which means it always had water. Okay? But organic reactions don't always have water. So we have to change the definition of acid and base. So when we change the definition acid and base, we're going to talk about what we call Bronsted-Lowry acids and bases. Okay, so in this case, we have a proton, a hydrogen, an acidic hydrogen, is going to move from the acid to the base. Okay, so we're still moving a proton, but we don't have to have water. So let's talk about that just in a general concept. So the first thing we want to say is that an acid is something that donates a proton. So if we look at our classic acid right here, HCl, and I'm going to draw the lone pairs around this HCl just so you see them. In fact, I am going to put the bonds between the H and the Cl. H and Cl. Okay, so remember that bond is 2 electrons that we're having between the hydrogen and that chlorine. And we're going to call that our acid. And in this case, we're going to call NH3 our base. Okay, so we didn't have water in here. We can have water, that's fine, but we don't have it. What's going to happen here is that these electrons are going to come over here and make a new sigma bond with that hydrogen. As that's happening, the electrons go back onto the other component that was donating the hydrogen. So the acid is the thing donating the hydrogen. The base is the thing accepting the hydrogen. okay? And so when we do that, the reaction maybe goes in equilibrium here, and we end up with Cl minus, because it has both of those electrons from that lone pair, from that bond, are staying on that chlorine, plus NH3, and I'm going to draw the proton that transferred over here. So this is our acid, because it gave the proton away. This is our base, because it accepted that proton. Now, can the chlorine by itself on the other side of that reaction act as a base anymore? No, it has no hydrogen to give up, but can it accept a hydrogen? Yes, it's got a negative charge. It can accept a hydrogen. So we're going to call this our conjugate base. And this has a proton it can get rid of, so we're going to call this our conjugate acid. Okay, so your acid always becomes the conjugate base. And because of equilibrium, if it's the conjugate base, it'll turn back into its acid. The base always becomes the conjugate acid. And because of equilibrium, it always goes back to its base. So we have that equilibrium going between the acid and the base. The acid and the conjugate base, and the base and the conjugate acid. Okay, so why is this important? Well, the first thing I want you to note is we don't actually take a proton without electrons around it and just fling it around the universe. No, these electrons from the base have to start forming the bond with hydrogen before it loses those hydrogens with the conjugate base. So guess what? We're pushing electrons around. We're using those two-pronged arrows to show two electrons are coming around to do work. That's how we show what's happening in mechanisms, okay? So acid always has a proton to donate, and then a base always has something to accept that proton. Usually it has a lone pair or a negative charge. So you can tell the difference between your acid and base, because your acid's going to have something with a hydrogen on it. Your base will usually have a lone pair or a negative charge. It's going to use that lone pair to reach out and grab that hydrogen. Okay, so can we use water in this? Well, yeah, so let's use water. And it has a hydrogen that it can give away, but it has two lone pairs too. And let's use this base again, right here. And can we get this to react as well? Well, yeah, water can now act as an acid and donate one of its protons to give us OH. And then the lone pairs are here and gives us a minus charge here. Plus, we get the ammonia structure again, 3 plus hydrogen. So what happened is these electrons came over here, started forming a bond with one of those two hydrogens, and got transferred to the now conjugate acid, and our water turns now into our conjugate base. So the thing that transfers the proton is the acid, the thing that accepts the proton is the base. Okay, so traditionally there's a lot of different things we can use for that. And in Gen Chem, we learned about the strong acids, HCl and sulfuric acid and nitric acid. Those are the ones we learned about, and those are all very, very strong right here. But in the context of organic chemistry, we tend to have slightly weaker acids, but we still transfer protons. So we have to identify them as such. And okay, good. So what we're going to see is in this table here is that we start with our traditional acids we've always, grown to love and have tattooed on our wrists. Anyway, but then we have to introduce what we call inorganic or organic acids. And the most common of those are going to be carboxylic acids. This particular one is acetic acid. It's our simplest, one of our simplest carboxylic acids. Okay, but that's not the only way to have an acidic proton on an organic compound. But when we have stuff that have these carboxylic acids, those are our organic acids. That proton is the one that's going to be transferred. Okay, so let's talk about bases and how to recognize our bases. Notice when I draw the Bronsted-Lowry acid name up here, it's H-A, okay? Because that bond between the H and the A is going to be broken when the proton gets transferred. And then if we look at our bases here, that B has a lone pair on it, because that lone pair is the lone pair that's going to reach out and grab the hydrogen. Okay, so look at our inorganic bases that we are familiar with. Hydroxide ion, we know that that's an inorganic one. This ammonia, but water can act as a base as well. And ammonia ion, the amide ion, can also act as a base. It has a negative charge and lone pairs. Notice every single one of those inorganic bases has a lone pair on it, whether it's neutral or not. Let's look at organic ones though. The nitrogen on this methylamine has a lone pair on it. It can act as a base. This 3 lone pairs on this oxygen anion acts as a base. Acetone is a base. That ketone is a base. It's a base because the oxygen has a lone pair on it. It can accept a proton. And here's the weird one. This is the one you got to wrap your head around. The lone pair, the 2 electrons in a pi bond count as a base. Not a sigma bond. The 2 electrons in a pi bond count as a base. So if you remember that, the sigma bond's 2 electrons, the pi bond's 2 electrons, we have those are going to there. So write that down. The pi bond counts as a base. All the other ones are fairly easy to recognize because the lone pairs are sitting out there and staring at it. But the pi bond can act as a base. Okay, so that works great if you're transferring a hydrogen. What if you're not transferring a hydrogen, but you're doing some kind of other transfer of those electrons? You're moving those electrons in a different way, okay? So we have a new word for this. We call it a Lewis base. A Lewis base is a electron pair donator. Okay, think about that. The Bronsted-Lowry base is something that has a lone pair that's going to grab the hydrogen. The Lewis base has a lone pair that's going to use those electrons to make a new sigma bond. So it has a lone pair to make a new sigma bond. Lewis base. Now, we have a new word for this. The new word is nucleophile. Nucleophile means positive charge loving. So I have a lone pair. I'm going to take this lone pair and try to find something that's partially positive or positive to react it with. So I'm searching for positive charge. I'm a nucleophile. I'm a Lewis base. Lewis base and nucleophile are equal terms. They mean exactly the same thing. Okay, 5 things that you can do in a mechanism was react a nucleophile with an electrophile. So now we've defined what nucleophile is. Okay, so let's think about a couple of the things that we'd see. Traditionally we'd see something like, oh, this hydroxide ion has those lone pairs and it's got a negative charge. So obviously it's a Lewis base, and it's going to use one of these sets of lone pairs to reach out and make a new sigma bond. But you can do that with neutral compounds too. Just if we change this to methanol, it also has lone pairs, but it's neutral and it'll react. And just like I said before, the pi bond in a double bonded carbon can act as a pair of electrons. It can act as a Lewis base. So that means all alkenes are nucleophiles. Okay, so neutral molecules can be nucleophiles. Charged things that are negative can be nucleophiles. All right, questions on that?
So the Bronsted-Lowry also donates.
Okay, Bronsted-Lowry acid or base.
Base.
Bronsted-Lowry base uses its electrons to grab a hydrogen.
Also accepts.
Right, it's accepting a hydrogen.
Right. Lewis base donates.
No, the Bronsted-Lowry base donates the electrons to accept the hydrogen.
Okay.
Okay, so that lone pair is reaching out and grabbing that hydrogen to make a new sigma bond hydrogen. So it's still using the lone pair is the thing that's doing base part. Does that make sense? That's a very critical fact,
So
actually.
the focus just changes on whether we're looking at the proton or whether we're looking at the electron.
The bases will always have those electrons reaching out to make the new single bond. The acids are going to be the things that are accepting those electrons. In the case of Bronsted-Lowry, it's always a hydrogen. But what I'm going to say next is that Lewis's are anything that will accept those electrons that aren't hydrogen. Okay? So it's still an acid because it's still accepting those electrons to make that new sigma bond, but it doesn't have to be hydrogen that is in Bronsted-Lowry. Okay, so that means that our thing that is accepting electrons wants electrons, which means it's an electrophile. It's searching for those negative charges, or there's partially negative charges. Okay, so the Lewis acid is the thing that the Lewis base uses its electrons to bond to. The Lewis acid is what the Lewis base uses its electrons to bond to. The Lewis base has electrons to donate. The Lewis acid has a reason to accept it. And most of the time we say it has a reason to accept it because it either has a positive charge, a partially positive charge. Okay? And so we can see that when we look at some of our Lewis acids. Okay, let's do this right here. Wait a minute, you just said that's a Lewis base. Well, yeah, it has electrons to reach out here, but it can also be a Lewis acid because it can accept protons to form charged species. Okay, so, but those are not, but it's also a Bronsted-Lowry acid too, right? It can accept electrons to form things. Oh, let me change that example. Yeah. Is that water has both the electrons to act as that Lewis base, but it can also accept electrons to act as a Lewis acid. Okay, but the most common ways to think about this are you're looking for partially positive charges, partially negative charges. Think about it. These bonds are polar, right? They're pulling electron density in toward the oxygen, sorry. They're pulling electron density in toward the oxygen. So we have a partially positive side of that bond. That partially positive side of that bond is the part that's looking for electrons. So how can we also look at these? Well, if we also have things that have a not full valence, we call these Lewis acids as well. Things like boron trifluoride or aluminum trichloride, they don't have 8 electrons in their valence shell. That means they can accept a pair of electrons to make its valence shell. So it's a Lewis acid. It's accepting a pair of electrons. Okay, so Lewis bases usually have a lone pair and or a negative charge and donates those electrons. Here, this part of the water is going to be accepting the electrons. This part of the water will be donating the electrons. Yes.
Real quick, so I noticed it says that all Bronsted-Lowry acids are Lewis acids, but the reverse is not considered true. So how can we tell if the Lewis acid is also a Bronsted-Lowry?
If it transfers a proton. Only if it transfers a proton. Bronsted-Lowry has to transfer a proton. Lewis acid, Lewis base can actually form a complex without transferring a single proton. That's the difference. Okay? So the definition for Lewis acid works for Bronsted-Lowry because electrons were used. Bronsted-Lowry doesn't always work for Lewis because you have to transfer a proton. But when we talk about this, if you just focus on the Lewis acid, Lewis base description, you can use it for all of your chemistry reactions, because one of our 5 things that happens in a mechanism is nucleophile reacts with an electrophile. Now we know what our nucleophile is, our Lewis base, and we know what our electrophile is, our Lewis acid. So nucleophile, Lewis base, electrophile, Lewis acid. We now know all 5 components that can happen in a mechanism. All right. So moving on from there, let's show you why things like that boron trifluoride can react. So let's see. All right, so if we have boron trifluoride, it doesn't have a full shell. So it needs to have 8 electrons to have a full shell. So it's one of those ones that kind of breaks the rule. It forms a neutral molecule with just those 6 electrons. But if it did fill its shell, it would have to accept 2 electrons, right? So what if we had something that we know can act as a Lewis base, and we know it can act as a Lewis base on the lone pair side? So what if we had these electrons come over here to make a reaction here? What would happen? Ooh. First of all, the boron would have a full electron shell, but boron would now have more electrons than it needs. So it's going to have a, if we did the formal charge on it, it's going to have a minus charge. And we have the oxygen over here, and we have the 2 hydrogens haven't gone anywhere. And we have 1 lone pair on the oxygen. One of those lone pairs on the water is making the bond with boron. The other one is still on the oxygen. But if we calculated our formal charge for that, our oxygen has 3 bonds to it and only 1 lone pair. So it actually has a positive charge on it. So no proton was transferred. Electrons were used to create a new sigma bond. Lewis acid, Lewis base. Questions? Okay. So the boron did not have a full shell. It is searching for electrons. The boron trifluoride is the electrophile. The water has 2 lone pairs to share. It's looking for positive charge. It is the nucleophile. All right. So what I'm going to end up doing is I'm going to end up moving away from this and just saying nucleophile, electrophile. So just have that in your head what the Lewis acid base and a nucleophile, electrophile means. All right, questions on that? Nothing in the chat so far. All right. So let's go and think about this in more of an organic chemistry way, okay? So what we'll see for a lot of times is we'll have things that have charge or things that might be neutral. So let's think of something that has a charge and go with a carbon, CH3, CH3, CH3. And let's say we had something on that carbon and we did that the heterolytic cleavage, and we broke a bond to give it a positive charge. Okay, right there, positive charge. What does positive charge mean? Is it a Lewis acid or base? It's an acid, it's an electrophile. It's looking for electrons. It has a positive charge. All right, so this is our electrophile. And let's say we have something that it wants to react with. And the thing that it wants to react with has to have electrons, right? So let's do the 4 lone pairs on boron. Bromine. Ugh. 4 lone pairs on bromide ion. Okay, what does that mean? That means that our Lewis base is our bromide ion because it has all those electrons to play with. And if these electrons were to come in here and react with that positive charge, we'd end up with a new sigma bond. Okay. So that's the important factor we see in a Lewis acid reacting with a Lewis base, a nucleophile reacting with electrophile. Electrons are used to create that new sigma bond, okay? So we can create one bond there, or we can actually do something different. We can take this compound here, and first of all, is this an electrophile or a nucleophile? Got a pi bond. Right, so it is the nucleophile. It is the thing with the electrons, right? So we have this right here. Okay, so this is a Bronsted-Lowry acid. Okay, so, but it's also a Lewis acid because it has a polar bond right here. This is the partially positive side of this molecule. This is the partially negative side of this molecule. This is looking for positive charges. Where is it going to attack? It's going to attack the hydrogen or the chlorine? The hydrogen, because it's the partially positive side of that. So this is our Lewis base because it has the electrons. This is our Lewis acid because it has a partially positive charge. So these electrons are going to reach out and grab that hydrogen. These electrons are going to go back here, and we're going to create a new bond with that hydrogen. And it turns out we're going to end up with a positive charge over here, plus chlorine. What happens to these electrons? Oh, they went and stayed on the chlorine. So we're going to have a total of 4 lone pairs on the chlorine and a negative charge. Cool, this is looking like organic chemistry now, right? We had the Lewis acid, which is also a Bronsted-Lowry acid here, react with our Lewis base, the alkene, to create a new sigma bond and give us this compound. Now, so this is our new bond right here. The electrons from that pi bond are the ones in between that carbon and that hydrogen.